Okay, so let's get started. The last time we were looking at areas under curves, and we approximated those areas using rectangles, and then we allowed the rectangles to become infinitely thin, which is equivalent to taking infinitely many rectangles, and that gave us an area. So that technique is known, that kind of integration is called Riemann integration or definite integration. And those sums that you come up with that you then let n go to infinity, those are called Riemann sums. So we're going to make things, we're going to specify some of the notations and the terminologies for the sorts of things that we were doing in the last session. Okay, so definite integrals are used to find the area under the graph of some function. We have a closed interval from a to b, f maps a
सर
to
मेरे
b.
से पहले वाला सिलेबस आ रहा है मिड फाइनल टर्म में
Yes, the area
मुझे
under the
समझ नहीं आ
graph.
रहा मैं आज मैं पहली बार क्लास ले रहा
Is there another question? Okay, so the area under the graph of f, which maps a to b to the reals, that's found by what's called a definite integral. And note that areas under the axis are taken to be negative. So remember, the height of a rectangle, you said, okay, I'm taking x to be this value, and then I'm taking y of x to be the height of the rectangle. Well, if y is below the x-axis, right, then that area would be considered to be negative. Okay, so your definite integrals could give you a negative number also. Um, so this notation is used to mean the area under a curve. So f maps the closed interval from a to b to the real numbers, and then we want the area under the curve of under the graph of f as x goes from a to b. Okay, so this is the notation for that, and it bears a resemblance to the notation that we had for indefinite integrals, and we'll see the reason for that a little later. But this is the notation for that. Okay.
Sir, I have a question.
Yes.
Sir, is the Riemann sum just for our understanding or like understanding the concept या फिर इसके questions में आएंगे? Will we be asked to actually do it?
Yes.
Okay.
Okay. So remember we discussed the area of a triangle, right? So it was bounded at the top by the line y is equal to x, and then the side was at x is equal to 1, and the corner was at x is equal to 0. So that area that we found was the area under the graph of y equals x as x goes from 0 to 1. And we found that that area was equal to 1/2.
حمود حمود
Okay.
حمود حمود
That was
حبيبي حمود حمود حبيبي حمود حبيبي حمود حمود حبيبي حمود
that was
حمود
the result
قوم
that we
اقعد من النوم قوم اقعد من النوم قوم اقعد
that was
من
the result that we had before. Okay. Now, the sums that we were using are called Riemann sums. So let me be a bit more, give you the notation and the nomenclature for those. So we're asked if we're going to do integration by Riemann sums, then we have to represent this area. This is the area under the graph of y equals f of x from x equals a to b. We're trying to find that area, and we find that area using Riemann sums like we did in the previous session. Now, remember, we took the limit as the number of rectangles went to infinity. So limits don't always exist. So this is the area under the graph of y equals f of x from x equals a to x equals b, if this limit actually exists, if this definite integral actually exists. Okay, so what we did last time, let me remind you, you fixed a point at x, which we call x0 at
حمود
a.
حمود 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 حبيبي حمود حمود حبيبي حمود حبيبي حمود حمود حبيبي حمود حمود
क्या ना करो यार
دورك على مين النار
Then you had the n point. So if you want n rectangles, then you need n subintervals, and you need n plus 1 points. So we call those points x0, x1, x2 up to xn. Okay? And the left end point of the interval is x0. The right end point of the interval is xn is equal to b. And we've got these points x1, x2, and so on up to xn minus 1 in between the endpoints. Yes, there's a question?
Yes, sir. I wanted to ask that what is P here, the set P? What is this?
That's the set of points which give you the left bottom corner of the rectangle and the right bottom corners of the rectangles.
Okay, sir.
So you're going from A to B, and you go from A to B putting in n plus 1 points so that you can have n rectangles.
Okay, sir.
So these are n plus 1 points that run between x0 equals a and xn is equal to b. Okay? And then these points divide the interval a to b, the line segment on the x-axis from a to b. They divide them into n subintervals. Okay? And those n subintervals are the bottoms of these rectangles that we've been talking about. Okay? So this this set of points is called the partition. Okay, and the one notation that we use for how fine the partition is, whether it's a coarse partition or a very fine partition, is to look at the maximum length of one of the subintervals. So xi plus 1 minus xi is the length of the ith subinterval, and you can see which one of these is the biggest. Okay, actually,
Sir,
that would be the I plus 1 subinterval.
Sir, the partition is basically the width between the bottom
Partition is
corners
the
of the
set of
triangle.
points. The partition is a set of points from A to B, running from A to B on the x-axis.
Okay.
Okay.
Sir, what is this notation you've used for P over here? These double modulus
The
things?
norm of the partition.
Okay.
All right. So the width of the ith rectangle is xi minus 1. You can write that maybe as delta I. Okay. And what we do is we take these points, zeta I, and these are points which lie in the interval from xi to xi minus 1. So the subinterval xi to xi minus that runs between xi and xi minus 1. I should have written those in the opposite order. I'll fix that in the notes. That's the base of the subinterval. Now that's the base of the ith rectangle. And within that base of the ith rectangle, I want you to pick a point zeta I. Okay? And what we do is f of zeta I then is the height of the rectangle. So you pick a point where you evaluate the function, and whatever the function value is, you make that the height of the ith rectangle. So if you ignore the sum for a minute, you just look at f of zeta I times xi minus 1. Okay? F of zeta I is taken as the height of the ith rectangle, and xi minus 1 is the width of the ith rectangle. Okay? And then you have n
Sir,
rectangles.
so
Yes?
Sir,
sir, is zeta I the midpoint of
Okay,
this
right.
width?
So the idea is that it shouldn't matter. Okay? You can take the left endpoint, you could take the right endpoint, you could take the midpoint, you could vary them as you like. But this gives you an estimate of the area under that curve. Okay?
So it's any. Okay.
Yeah, it's any point between xi minus 1 and xi. That's zeta I. Any point in between those 2 points. Right? So that's any point on the bottom of the ith rectangle. And then f of zeta I is how tall you make your rectangle. Okay? Then you add up all those rectangles. And you add up the areas of all of those rectangles. And hopefully that gives you a reasonable estimate of the area under the curve. Okay? So this S is called a Riemann sum. Okay? Right? So now, if this area under the curve actually exists, right? If the area under the graph of that function actually exists, then the area under the graph of f of x from x equals a to x equals b is the limit as the norm of the partition goes to 0. That's the same as the limit as the number of rectangles goes to infinity. So the limit as n goes to infinity. Summation I equals 1 to n of the areas of the ith rectangle, which is f of zeta I, xi minus 1. Now, yeah, there's a question?
Yes, I think someone asked this before, but I don't know. I don't get what norm of the partition is.
Okay, ignore that. Just think of this as the limit as the number of rectangles goes to infinity. Okay?
Oh, okay.
All right. So summation I equals 1 to n. F of zeta I is any. There's more questions? Yes?
Yes, sir. What it was that is zeta I is it the height of the rectangle or something?
No. F of zeta I is the height of the rectangle. Zeta I is a point on the bottom of the rectangle, of the ith rectangle, anywhere between the left endpoint and the right endpoint, anywhere between the left bottom corner and the right bottom corner of the ith rectangle. You have to pick some zeta I.
So f of zeta I will give us the height, right?
And that's how high we draw our rectangle. Yes.
Okay.
Last time we were taking zeta I as either the left endpoint or the right, either the left bottom corner of the rectangle or the right bottom corner of the rectangle. Right? But in principle, you could take it anywhere, and it shouldn't matter. Right? If there is actually if the idea of an area under the curve actually makes sense, and we can define functions for which it doesn't make any sense. If the area under the rectangle actually, if that idea actually makes any sense, then it will not matter which point you take. On the other hand, if you actually have to, we'll find an easier way of evaluating these things, which doesn't require thinking about rectangles. But if you are stuck with trying to do trying to evaluate the integral from first principles using rectangles, then it might matter for the ease of the calculation which point you take. So for that reason, people often take the left endpoint or the right endpoint. But in principle, it should not matter. Okay.
So we can take the midpoint as well.
All right. So I could have taken zeta I is equal to xi. I could have taken zeta I equals xi minus 1. I could have taken zeta I equals xi plus xi minus 1 over 2, the midpoint, or any other point. Okay. All right. There are more questions?
My question you just answered my question right now.
Okay.
I just wanted to ask you whether we can take the midpoint as well.
Yeah, okay. Take the midpoint. Take the 3/4 point, any point. You can take a different, you could have a different rule for each rectangle if you wanted to. In principle, it should not matter. Okay, so now let's see what that would mean. So you have x equals a to x equals b, f of x dx. Let's suppose that that area actually exists. Let's say that we want n rectangles of equal width. Okay, right? Didn't have to be. You could have picked your xi in the partition in such a way that the rectangles were not of equal width, but it might be easier to do it if it was of equal width, right? So then if we're running from B to A, and there are n rectangles, then the width of every rectangle is the same, and we want the width of every rectangle to be the same, then the width of each rectangle is B minus A over N. Okay? So you can come up with all sorts of Riemann sums to evaluate an integral, but this is perhaps the easiest way, is to say all the rectangles will be of equal width. Okay? So then if the overall length is B minus A, then the width of each of the n rectangles is B minus A over N. Okay. Any questions? All right. And we're going to take our partition. We will take our partition. We will allocate the points for the partition accordingly. We will allocate them in such a way that the distance between each point will be this delta is equal to B minus A over N. Okay. So the way we do it is we have, again, our partition is x0 equals A, x1, x2, and so on, xn minus 1 up to xn is equal to B. And the way to do it in such a way that the distance between each of these points in the successive points in the partition is to say that xk is equal to A plus k times delta. So that means that x0 is equal to A, x1 is equal to A plus delta, x2 equals A plus 2 delta, x3 equals A plus 3 delta, all the way up to xn is equal to A plus n times delta, where delta is this width B minus A over N. Okay. Any questions? All right. So
Sir,
one way to, yeah.
Sir, can I ask a question? Okay.
Yes.
Sir, so basically delta is the length of width of the one triangle, one rectangle.
Yeah.
Yeah, and the width of the all rectangles are the same.
Yeah, and I've decided that it's just easier if all the widths are the same. Yeah.
Okay, sir. Okay.
Okay. So that means I can take my, I can take these, the point in the kth, in the base of the kth rectangle, or the kth interval, I have to pick a point zeta k, right? And I could pick any point I wanted to, but let's suppose that I will let that point be xk. So that's the right bottom corner of the rectangle. Okay? And we already said that xk will be equal to A plus k times delta. Okay. Right? I could have also have taken A sub k minus 1, and that would be A plus k minus 1 times delta, or I could have taken any point in between those 2 points. But, you know,
So,
just, yeah.
What's xk here?
xk is the kth point in the partition, which would be the bottom right corner of the kth rectangle.
Okay.
Okay. All right. So let's put that all into our formula. So let's say the Riemann sum using n rectangles, which is going to approximate that integral, is equal to summation k equals 1 to n f of zeta k xk minus xk minus 1. Okay, that's the general formula for a Riemann sum. In our particular case, we're going from k equals 1 to n, f of, what's my zeta k? I decided that zeta k would be the right bottom corner. So zeta k is equal to xk, which is equal to a plus k times delta. So that's f of a plus k times delta, times this width. Every rectangle was made the same width, so times the width, which is delta. Okay. Okay, summation k equals 1 to n, f of a plus k. Now what was delta? It was b minus a over n. And again, delta was equal to b minus a over n. Okay. Okay, so that is the Riemann sum. Now the actual integral is the limit as the number of rectangles goes to infinity as they become infinitely thin. So that summation k equals 1 to n, f of a plus k times delta was b minus over n, b minus a over n times the width delta, which was b minus a over n. Okay, so if you want to evaluate the integral using a rule that you have rectangles of equal width, and you're going to calculate the height of the rectangles using the bottom right corner, that's where you're going to evaluate the function, then this is the result. Okay, it shouldn't matter which point you're using on the subintegral. If it does matter, then the integral doesn't actually exist in this sense. Okay. All right. Now, what do you think it would be if instead of using the bottom right corner of the rectangle, and that's where you do your function evaluation, what if you use the bottom right corner? Here we've used the bottom right corner. What if you use the bottom left corner? So this is a right-handed rule. What if we used a left-handed rule? What would
K
change?
minus 1.
Yeah, k would become k minus 1. That's all that would change, okay? So you would get this. And again, limits don't always exist. Maybe that limit doesn't exist. And then we don't have an area in Riemann's sense of area under a curve. Okay. Now, I'm going to give you some properties of definite integrals, which might be useful later, right? So remember you had properties of indefinite integrals, which said that you could pull a constant outside, and things like that. So, and we had properties of limits and derivatives. So there's also a set of properties for definite integrals, which you can use to maybe make their evaluation a little bit easier. Okay. So there's a linearity property. This should hopefully remind you of a property that you've seen before. We said that if your integrand was alpha f of x plus beta g of x, then you can break a sum up into two pieces, and you can pull a constant outside of the integration. Okay. So you should try and think about what this means in terms of areas. It looks very much like the property that we had for indefinite integrals also, right? So suppose, remember, again, the area of the triangle was given by this integral x equals 0 to x equals 1, x dx. That was, we said that was equal to 1/2. So if the integral goes from x equals 0 to x equals 1 under the curve given by y of x equals 3x dx, then what's the answer?
3/2.
3/2. We can pull the 3 outside, and then we can evaluate the integral. Okay. Now, the integral of from a to b of 0 dx, right, is 0, right? And one way of looking at that, if you want to think in terms of rectangles, each rectangle is going to have a height 0, right? Right. Wherever the points are zeta I that you evaluate the height of the rectangle, that height is 0. So the Riemann sum gives you 0, and then in the limit is whatever number of rectangles you take, and then in the limit as n goes to infinity of 0, you get 0. So the
Sir,
integral, if a function is 0 from a to b, then its integral from a to b is 0. Okay.
sir, so can
Yeah.
you go back to the previous slide number 24?
Yeah.
Only 23, one slide back.
Okay.
Sir, so here alpha is zeta I.
No,
Alpha and beta is R.
alpha could be any constant, any real constant. Alpha and beta are real constants here.
So they are not the height of rectangle.
No.
Okay.
Okay. Another rule. Odd functions over symmetric intervals. And what's an odd function again? It's a function such that f of minus x is equal to minus f of x. So a function like x or x cubed is an odd function. Sine of x is an odd function. Okay. So if f is
So what's an
odd,
odd function?
Hmm?
What's an odd function?
An odd function is a function such that f of minus x equals minus f of x. Okay. Now, if a function is odd over the interval from minus a to plus a, and then it's the area under the curve is 0. So basically what happens, if you think about the sine function, for example, as you're going from minus pi to plus pi. So from minus pi to 0, all the area is under the curve. And then you have the exact same area except it's above the x-axis. So the positive and the negatives cancel each other out. Okay? So if you have an odd function, that's a function such that f of minus x equals minus f of x over a symmetric interval. That looks like the interval from minus a to plus a, whatever a is. Then the area under the curve from minus a to plus a is equal to 0, right? The positive and negative area rectangles are canceling each other out, basically. Okay. So if I gave you this, right? Sine of 135x will be odd. Then, so this is an integral over us. This is an odd function being integrated over a symmetric interval. So that's going to be 0. You really don't have to do any work. Okay. Okay. Another property. If you're thinking about the function being defined over an an interval from A to B, closed interval from A to B. And it never takes any negative values. Okay? Then the area under the curve will always be greater than or equal to 0. That's why, because the rectangles all have non-negative heights. So if you add up all those areas of those rectangles, you won't get any negative numbers in there. So you can't get a negative answer. Okay? So if you integrate a function which only takes non-negative values from A to B, then the area under the curve will always be greater than or equal to 0. Okay? Sometimes it is very difficult or not possible to exactly evaluate an integral, but if it's important to us for some practical reason, then we at least want to be able to put bounds on it. So it's good to know if we can, if the result is expected to be negative or not. That's a property. Okay, so what about this? Integral x equals 1 to x equals 136, x over x cubed plus 1 dx. What can I say about this integral? I don't know how to
It's
evaluate it exactly.
always positive
Yeah, so
or
the
zero.
the integrand, the function x over x cubed plus 1, is greater than or equal to 0 everywhere between 1 and 136. So I know that integral, that the area under that curve, is greater than or equal to 0. Okay. We can also compare integrals. So supposing that we always know that the value, you have an interval from closed interval from A to B, you know that the value f of x on this interval is always less than or equal to the value g of x on that interval. Then that means that the area under the graph of f is less than or equal to the area under the graph of g. Okay? And if you just imagine drawing a graph, so one graph is higher than the other, then the area of the one which is higher should be greater than the area of the one which is lower. Okay? So you can sometimes, again, it can be difficult to evaluate an integral to get its value exactly, but you may be able to compare it to another integral which is easier to evaluate. And so at least you can get some bounds on how big the integral is. Okay, so.
Sir?
Yeah.
Sir, can you go back to the previous slide? Number 30. Okay, sir, I didn't get the point that if two graphs are starting from the same point and ending on the same point, so how can their area can be different? You say that area of f of x is less than the area of g of x. They're starting from the same point, both are starting from A and both are ending at A. How can the areas can be different?
No, both of these functions are defined on the interval from A to B. And g of x, the graph of g of x, is higher up on your graph paper than the graph of f of x. So the area under g is bigger than the area under f.
Okay, sir. Okay.
All right. So the integral from x equals a to x equals b of the constant function 1 should be less than or equal to the integral from x equals a to x equals b of the constant function 2, for example. Okay, slightly less trivial example. Supposing I've got x over 1 plus x squared. All right, I want the area under that function from x equals 1 to x equals 2. And I claim that area should be less than or equal to the area under x plus absolute value sine of x over 1 plus x squared. So what's the argument there? If I compare the two functions, the numerator function is always bigger than or equal to the numerator function here, and the denominator functions are the same. So this function on the right-hand side, the integrand, always takes greater values on the interval from 1 to 2 than this function, this integrand on the left-hand side. So the area under this curve on the right should be greater than or equal to the area under this, the graph of this function on the left. Okay, what if perversely I ask you to find the integral of some function from a to a? So I say, what's the integral from x equals a to x equals a of f of x dx? So let's decide that that's going to be equal to 0. Why? Because the triangle, the rectangle that you're going to try to draw has 0 width. So it has 0 area, okay? So the Riemann sums that you're going to come up with to do this involve a single rectangle which has 0 width, so it has 0 area, okay? So our convention is that if you take the integral from x equals a to x equals a of any function, dx, that will be equal to 0. Okay, so here's this horrible integrand. I don't know how to. I wouldn't actually know how to evaluate the integral using rectangles, except it's over a 0 length interval. The interval is going from x equals 2 to x equals 2, and so I don't actually have to do any work. I know that that's equal to 0. Okay. All right. Okay. Now, suppose that f is integrable from a to b, and c is something which lies between a and b. C is a point from a to b. So this rule is saying that if you want to evaluate the integral from x equals a to x equals b under the graph of f, you can take the area from x equals a to x equals c, and then you can add the area from x equals c to x equals b. And those two areas add up to the total area. Okay? So this can be useful when you have a function and its behavior changes as c. So if you have a function which is defined in 2 pieces. So from a to c, it's behaving like this. And then from b to c, it's behaving in some other way. And now you're asked to find the area under the curve of f, under the graph of f. Well, what you can do is you can evaluate the area from a to c, and then you can add the area from area under c to b. You add those two together, and that will give you the total area. So if it's convenient, you can break up the interval of integration into 2 pieces. Okay, so for example, let's say f of x is equal to -1 for x greater than or equal to 0. And it's equal to +1 for x less than 0. Now I want to evaluate the integral for the area under the graph of f from x equals -1 to x equals +3. So how would I do that?
So you can break it.
0 and 0 to 3.
-1 to 0 and then 0 to 3.
Yeah, I could say this is equal to the integral, the definite integral from x equals -1 to 0, f of x dx. plus the integral from x equals 0 to x equals 3 of f of x dx. And then in the first integral, the integrand would be plus 1. And in the next integral, the integrand would be minus 1. So for one integral, the heights of the rectangles are all plus 1. And for the other integral, the heights of the rectangles are all minus 1. Okay? So that would be much easier to do. All right. Order of integration. For some applications, this might seem a little arbitrary right now, but for some applications, we want to flip the order of the integration, right? So when a is less than b, we would write integral from x equals a to x equals b, right? So b is bigger than a here. Supposing that I say, no, I want the integral from x equals b to x equals a of f of x dx, despite the fact that b is bigger than a, okay? So the convention is that that's the same as the integral from x equals a to x equals b, and you pick up a minus sign. So it's minus the integral. If you change the order of the integration, then you have minus the original integral, okay? And one way of thinking about it is that means you're taking the points in the partition in the opposite order, okay? All right, or you can just say that's the convention that we use. So we had integral x equals 0 to x equals 1 of x dx. We already found that was equal to 1/2. That was the area of the triangle. Okay. So what if I asked you that I want the integral from x equals 1 to x equals 0? I change the order of the integration.
Minus half.
It will become minus 1/2.
It will become minus 1/2. Yeah. Okay. All right. So that's it for this session. Those of you who want to should stick around if you have any questions. Otherwise,
Sir, any update on the result of the mids?
yeah, I'm still marking. It's taking
Okay.
forever.
Sir, I have a question.
Yes.
Sir,
Sir, do we
Please ask
have a
your
midterm? Do we have a next midterm, or it will be only a final left?
I think there's only the final left.
Okay.
Sir, how do you suggest we prepare for the finals? I mean, in the midterm, the questions were more about proofs than numerical questions. So how do we prepare for them?
Well, study everything. Right?
Can we get like appropriate questions to practice, because the web work was really different from what we had in the midterm.
Yes, the web work and the questions we do from the book, Thomas and Finney, they're all more numerical in nature.
So where can we practice, for the final?
If you want more, I suppose if you want more conceptual problems, then one book is Adams' Single Variable Calculus.
Okay, sir. Sir, is the final going to be like the midterm?
I don't know. That's in the far future for me.
Sir, it's not very far.
Sir, are you gonna make it or somebody else? Because
we all get together and make some questions, right? So,
sir, can we know who had the major share in making the question for the mid?
everybody contributed something to this mid.
Could you not make it like the mid?
No, the final will try and test concepts, and we'll use whatever questions we think test the concept.
Sir, will the final include the syllabus from the midterm, or will it be after, like the syllabus we have studied after the midterm?
No, it'll include everything because you know we've done some limits now, but there'll be more limits to do later, and it's difficult with mathematics. It's difficult to disentangle things because there are concepts that keep being used throughout the course.
So what is the
So
rough date for the final?
I think it's 27th or 25th.
Yeah, I mean, I think it'll be on your Zambio, right?
sir, can you repeat the name of the book you had just mentioned, Adam?
Yeah, Adam's single variable calculus.
Sir, can you please explain this last part again?
The last part? This
ये
slide?
जो the negative one equal to the positive one. Yeah.
Yeah.
This
Yes.
one.
So the idea is that on the right hand side, I'm going from x equals a to x equals b. So I would be taking the points in order x0,
Oh,
x.
all right. Okay. Yeah. I get it now.
Sir, I have a
Thank you,
question.
sir.
Yes.
Is it possible that we get an email or a notification on LMS or something like that when an assignment is uploaded on WebWork? Because
Yes,
sometimes
sir. Yes.
it really happen and assignments get missed out.
Okay. All right.
Sir, please consider this because.
Yeah. I'll do that for them.
Okay.
Sir, could you please explain the norm of the partition? What was that?
Oh, that's just telling you. Okay, so if I consider all of the differences, xi minus 1, right? So I have these points xi in the partition. I consider xi minus 1. That's the width of the ith rectangle, right? So the norm is just how big do the widths get?
All right. So
Right.
in
So
our
letting,
example,
yeah. So in our case, the easiest way is to let all the widths be the same. So the norm of the partition is this delta, b minus a over n.
okay, all right. And in the case where the widths are not equal, then what will be the norm?
The biggest width.
Okay, got it. Thank you.
Okay.
Sir?
Yeah.
Sir, how accurate is the answer we get from the integration from the Riemann-Simon?
Yeah. That's actually an entire field of mathematics. So
like I don't get it where like I get it like we take off 0 to -1, but since that 0 isn't included in that option, like it's when smaller than 0, so it could be minus closed limit approaches 0. So I'm just confused why we take from 0 to 1.
Okay, so you're looking at a particular question?
Just this one.
Which one? This one?
Yeah, this one. Yeah, we take from 0 to -1.
Okay.
But since
Okay, so think about the graph of the function for a second. You're taking for negative values, you're taking +1, and then when you hit 0, you start taking values -1, right?
Yep.
Right. So now, if you want to do this, you would go from -1 to 0 with a height of +1. So that area would be +1, right?
Yes.
And then the next one, you would go from 0 to 3, and the height is -1. So that integral would be 3 times -1 is -3.
I get how we do this, but I just don't get like I actually have this confusion from the limit part as well, that when something isn't included in that portion, like when it is less than 0 and we don't have the equal sign, why do we take from 0 to 1?
Oh, yeah. Yeah, actually, that's a very deep question. Um, um, and the answer is that if you go more deeply into this, that single point doesn't matter. The value of f at a single point doesn't matter. I could do this. I could say this is -1 for x greater than 0. This is +1 for x less than 0. And I could say f at 0 is equal to 37, let's say. And that f at 0, just by itself, doesn't contribute anything.
Oh, I
And
get
that's
it,
because
sir.
the technical answer is that a single point has measure 0, and it will not contribute anything.
I get it, sir.
Okay.
Sir, did you upload the previous recorded lecture? I don't think you did.
I think I did.
Okay, okay, I'll check it again.
Yeah, I mean, check on the YouTube.
Okay.
If you can't find it on the OneDrive, it's on the YouTube for sure. Okay. All right. Any other questions? Okay. I will see you next week then.